All right, so this is our second lecture on chapter 14, aqueous equilibria, acids and bases. So we talked before about pH and how the pH scale basically works. And here we're talking more about how we could measure pH, right? Conventionally, before people had like a pH meter, they would use an acid-base indicator whose color would change in some pH range, so they could actually make a measurement of what the pH is approximately based on some relative indicator chemical. These chemicals are themselves weak acids or weak bases, and they have the color changes between their starting form and their conjugate form, whether that's a conjugate base or a conjugate acid. And so we got an example here of some typical ones. You won't have to memorize these, but typically you'd want to pick something that's close to whatever it is that you're wanting to examine. Like if you're trying to examine a range between like 6.0 and 7.6 here, they say that like you could use bromothymol blues. Some indicators have multiple pH color changes. Some of them have two different ranges. Some of them change and have like an intermediate color that you can see. Many don't. Many of them are not as continuous as others. They're pretty clearly one, and then you cross some threshold and then they just change entirely. That can be advantageous, but it depends on what exactly you're trying to do. Sometimes they'll mix together different indicators. They'll call this like a universal indicator that'll have different colors depending on the pH if you put them all together. But typically nowadays people just use a pH meter. There are also pH strips, and they work with indicators attached to the substrate of the strip, so they can also change color to indicate. But you tend to get better measurements from a pH meter because it's fundamentally electrical in nature. The hydrogen ions themselves interact with the electrode inside, and that's how it's able to measure the changes. It has an ion selective electrode that's only affected by hydrogen ions. You can build them that are affected by other positive ions, but the way a pH meter is built, it measures hydrogen ions, and they're affected electrically on the system. So you tend to get more accurate, more reliable, better reproducible numbers with a pH meter compared to any other kind of indicator where a person has to look at a color and make a judgment, and that's always a little bit suspect. So strong acids and strong bases. So this is where we're going to get into the distinction between strong acids, strong bases, and weak acids and weak bases in a little more specificity, and kind of bring in the equilibrium concepts a little more tightly, right? Previous lecture was a little more of like a review of concepts. Most of that you should have heard before, maybe a little bit with the water properties, but here's where we're really going to start delving in, right? So if you have a strong monoprotic acid, the pH is easily calculated from the H3O plus concentration. Since it dissociates completely, the concentration of this acid that you start with will be the same as the concentration of the H3O plus you'll end up with. So that means that we can just use that concentration of acid to directly convert that into the pH. And we'll do that in some problems. This is true as long as you have a strong monoprotic acid and that's all you have going on. Okay? Calculation of the pH of H2SO4 is a little more complicated because essentially 100% of the H2SO4 molecules dissociate to give H3O plus and HSO4 minus. But this HSO4 minus is a weak acid, so as long as there's a lot of H2SO4 present, this doesn't dissociate very much, and so it essentially acts like a monoprotic strong acid, and this weak acid part is overwhelmed. But it does become more significant in weaker, less concentrated solutions of sulfuric acid. The contribution of HSO4 minus increases. We'll talk a little more about that later. With regard to strong bases, they're typically alkali metal or alkali earth metal hydroxides, most commonly being something like sodium hydroxide or potassium hydroxide. These are also Arrhenius bases, and they dissociate 100% as well and donate hydroxide to the solution. And you can calculate their pH readily from the OH minus concentration, and we'll do that in an example. They talk a little more about the other metal hydroxides, magnesium, calcium, strontium, and barium, and I'll look at those in some other examples, but many of these have solubility problems. Magnesium and calcium in particular are not very soluble, and that causes problems. They would be strong bases, but they don't dissolve very well in water, so they don't act like strong bases in terms of how they can contribute to the solution, since their dissolving has to occur before their dissociation. This is a more complicated idea we'll touch on a little more in the next chapter as well, but keep that in mind, and we'll look at some more details on that. Alkali earth oxides are even stronger bases because this oxide ion is a stronger base than hydroxide. But the issue with these is they're typically not considered conventional strong bases. They don't show up very often in test questions or examples, but it's something else to keep in mind that these are immediately converted to hydroxide whenever this peroxide ion exists in water. So it acts as a strong base. Again, though, there's some solubility issues with these things like limes and calcium oxides and hydroxides. So when they interact with water, they can form hydroxide ions, but getting them dissolved can be an issue. And again, that plays a role in why these things can even exist, despite how strong a bases they are. If they were that strong, they'd immediately just be pulled into water and dissociated because it'd be such a more stable place for them to be. For example, strong bases like sodium hydroxide and potassium hydroxide, if you take the little pellets and you just leave them on a table, they'll spontaneously hydrate. They'll get wet from the moisture in the air because that lowers their energy state by just having them exist as ions. That typically happens to strong things in very concentrated solutions. They tend to hydrate themselves to lower their energy state. That's something else to keep in mind when you talk about systems like this. So I've made a list of the 7 conventional strong acids and 7 conventional strong bases. There are acids that are stronger than these, but you don't commonly see them in problems as strong acids because when they make contact with water, they immediately act like all the other strong acids. And they're typically too expensive to use. Similarly with the strong bases, these are the ones that are conventionally seen. So with the 7 strong acids, you got your binary halo acids. So that's the halogens except for fluorine because hydrofluoric acid is weak. HCl, HBr, HI. Then you have H2SO4, and that's for its first ionization. The second loss of a proton is not strong. HNO3, HClO3, and HClO4. Sometimes they don't include both of these because sometimes they consider one to be so strong it's not conventionally strong anymore, but I'm including all of them because you do see these show up in problems, and you should know that these are strong whenever you see them because it'll allow us to do a lot shorter math to calculate things like the pH if you know that it's a strong acid. For example, same thing with strong bases. Most commonly you see sodium hydroxide or potassium hydroxide as your strong base when the book or an example is trying to show you a strong base. A reminder that lithium hydroxide, rubidium, and cesium hydroxide are also strong. Lithium has a little bit of solubility issues, but it's not that big of a problem. It still acts mostly like a strong base. For alkali earth metal hydroxides, strontium and barium are typically considered strong bases. They dissociate completely into 2 hydroxide ions, not 1. So they're like dihydroxyly strong. But the book doesn't really talk about this in much detail. And this, you won't see this coming up in too many examples. Know that magnesium hydroxide, though, and calcium hydroxide have significant solubility problems. Magnesium hydroxide is milk of magnesia, if you've ever seen it. It's just like a goopy kind of solution because the magnesium hydroxide does not dissolve very well. Calcium hydroxide, this talked about, is involved in the production of slag, lime, and other things where it precipitates out very easily. So these are prevented from being strong bases because they can't get into the water to begin with to become bases. So make sure you know this list because it will help you with sorting out problems, what kind of equations you need to use, and how you need to classify the systems that you'll see. So if I have the pH of a strong acid solution, I can just take the negative log of that concentration. Now keep in mind there are cases where the book or a problem or something will try to trick you. If these concentrations are low enough, like they're less than 1 by 10 to the minus 7, and you plug them into this equation like this, you'll get a basic pH, and that's not going to be possible if you start with an acid. Or vice versa, you'll get an acidic pH, and it's not possible if you have a basic solution. So although you can do this, you can just take this and plug it into your log. If you have a strong acid or strong base, you need to make sure that this concentration is above 1 by 10 to the minus 7. As long as that's true, you should be good to go. So since this is, 1 by 10 to the minus just 2-ish scale of numbers between 1 and 2, you're not going to see a problem. Like, this is okay to just go ahead and plug this right in here. The idea is that the starting amount of H3O plus, the 1 by 10 to the minus 7, has an insignificant contribution here because this is 1 by 10 to the minus 2. It's like 5 orders of magnitude bigger. So you don't have to worry about the contribution of the water's existing equilibrium with itself we can just kind of override it with a whole bunch of acid that we dump in there. Similarly to bases, it's the same idea when you have a strong base. Okay, just keep in mind there sometimes are trick questions where they give you very low concentrations, and if you plug this in here, you get a basic or acidic pH. And if that happens, you stop and the answer is just 7, because whatever you're adding doesn't affect the pH enough to really change anything. Sometimes they'll be even more clever and you'll need to add this concentration to 1 × 10⁻⁷ to fix it, to get a better number. But these are not commonly seen problems, so I'm not going to review them in depth. Just be aware that such things are feasible. Your typical example, though, you'll just take this concentration, plug this right in, and get a number. So they want us to calculate the pH of this 0.1 molar solution of NaOH. Now we could convert the hydroxide ion concentration into a H3O plus concentration, but the easier way typically would be to just go ahead and plug this in. If you plug this in, this is 10⁻⁻1 because it's a tenth. So you'd get 1, and then you subtract 1 from 14 and you'll get 13. So keep that in mind. There is an easier way to go about doing this one. Here, this is a slacked line, this is a base, but it produces 2 ions for each one. So we'll have to multiply this concentration by 2. Whoops. We'll have to multiply this concentration by 2. Let me get back there real quick. We'll have to multiply this concentration by 2, which they do, and then that's now the hydroxide ion concentration. We could work that out. If we did this, we'd get a pOH of 2 because this is a hundredth, and then we would be able to subtract that from 14 and get the answer. So that's another way to do this, or we could follow the approach that the book takes. These are typically pretty simple problems because you're able to get the answer by modifying this starting concentration, working with it, either plugging it in directly or making minor adjustments like multiplying it by 2 or something like that. So now we'll look at the final example. Now here we'll have to convert these grams to moles. We'll have to get a molar mass of calcium oxide. And we know that this peroxide ion is not stable in water and it converts into 2 hydroxide ions. So we're able to use that to calculate the pH again. But notice that we're able to modify the number of moles present in this solution in 1 liter. We got moles per liter here. This is really a concentration, right? And we're able to see that that's again a hundredth. So if we took the negative log of it, we'd get 2. We subtract that pOH from 14 to get the pH of 12. This is just how you could kind of do this, aside from this first part of division, mostly in your head, following through the basic logic of the problem. And you know it has to be basic because you know that this is lime. So you know an answer of like 2 is not possible. Make sure you're checking what you have the concentration of when you're doing these. I've noticed sometimes students rush through questions like this and they can get them wrong because they just plug something in and they don't go back and check was this an acid or a base. It's an easy correction if you have a base, but just keep that in mind. All right, so now we're going to get into the equilibrium. Now we're getting into the real meat of this. So let's say we have a weak acid. So these are not strong. This is a weak acid. It does not dissociate completely. So it has some relevant and finite, not really huge value for K. So we can define an acid dissociation equilibrium based on the dissociation equation that we've seen before. So Ka is equal to H3O plus times that conjugate base concentration over the HA concentration. Now, I'm going to introduce you to some equations in here that will make your life a lot simpler, but we have to understand the basic theory, where this is coming from before we can do that. These Ks are just like every other K, so it's an equilibrium process. That also means that it depends on the temperature, right? At a higher temperature, most acids and bases dissociate better. So typically, a hot solution will increase the value of Ka or Kb. Typically. It's not 100%, but it's typically the case. Because that action of dissociating, this reaction where a proton is transferred to water or a proton is removed from water, is typically endothermic. Okay, so a large value for Ka, okay, indicates a stronger acid than one with a lower value. Keep in mind that acids are often ranked by what they call their pKa. So that's the negative log of the Ka value. So if that's the case, then a really big number would have a really small value for the pKa. So the smaller the pKa, the stronger the acid. And some pKa's even go negative, which means they have a really positive value for their exponents and their Ka's, and so that'll mean they're even stronger. So small value for pKa means a stronger acid, and a larger value for pKa means it's a weaker acid. So sometimes you'll see them ranked that way. The way they calculate it is the same as taking the negative log of a concentration. You take the negative log of the Ka. And remember that if Ka is smaller, that means it's a weaker acid. If Ka is bigger, 10 to the minus 4, it's a less negative exponent, then that means it's a stronger acid. They give us an example of ranking these acids and their Ka's and pKa's, and they make a note, kKa is equal to negative log Ka. So you can see how we get a bigger number, that's a worse acid than one that's got a smaller number, and it's okay even for that number to be negative. That's okay. So they say they want me to calculate the Ka and pKa from this weak acid from the pH of the solution. So they give me the pH, and they want me to calculate these values. So we'll set up an ice chart like we did back in the previous chapters. So the initial concentration will be the concentration that they gave me, okay? And we'll assume that when we first added it, there was no H3O plus. We could say that there's 1 by 10 to the minus 7 in here. If we get small enough numbers, we can apply that as a correction. But generally, because this concentration is so big, and this is HF, which is a pretty strong weak acid, we're going to assume that the contribution from the water is negligible for now. There's no fluoride ion present. They didn't tell me about anything, so I'm going to assume that there's none of that present. The change will be based on the stoichiometry. So negative because there's a 1 in front of this, plus 1, there's 1 in front of this, plus 1 over here, there's 1 in front of this. We combine these together, subtracting x, and we can set up an equation for this, and we can get the concentration of H3O plus by taking the antilog and getting the concentration of H3O plus. That allows us to solve this setup example because now we know the value of x. So we can just plug all this in and calculate the Ka value. And if they want the pKa, that's just the negative log of that value. So again, this is just going to be an exponent input into your calculator using the E key or the capital E in the Google calculator to input these and then do the division, and you should be able to work this out fairly simply. In other cases where you don't have this much information, you might have to solve for x given Ka instead, and we'll see problems like that going forward from here. Calculating equilibrium concentrations, right? So they give us a sort of work-through process, right? First they say we have some acid, okay? And then they say in the next step that there's some transfer that takes place, okay? And these are the two equilibria that are currently in progress, okay, in this water solution. So this HCN goes to water and produces some hydronium ions and Cn minus, and it has a Ka of 4.9 by 10 to the minus 10. This process, which is just the dissociation of water, would be 1 by 10 to the minus 14, and there's basically 4 orders of magnitude difference between these two. So probably this dissociation of water is not important, but that's why they're having you do this comparison, so you can figure out which one is more important. 4 orders of magnitude, that's where they're getting this 10,000 here. So that's why they're not going to consider this second equilibrium. If this Ka is small enough or smaller than the Kw, then it just doesn't do anything. This acid dissociation is so bad that we might not even be able to say that a reaction happens. A measurable change in the pH actually occurs in real life. So here normally you add these two together. This is where, as I said, if you had a small enough value, you'd have to add in the H3O plus from the subsidiary reaction from the dissociation of water. But for now, we're not going to have to do that because there's 4 orders of magnitude difference. Then we can set up an ice chart, and we'll start with our concentration. This was given to us, the initial concentration of HCN minus, of HCN, and then approximately 0, 0, the change being minus x plus x plus x, and then we combine these two together to produce our equilibrium level here. Now sometimes you'll start with something over here, and that'll be in later chapters, and that will change. So it's important to set up the chart and learn how to set up these ice charts, ice meaning initial change equilibrium concentration, so that going forward, you have this as a great tool to help you organize the information from the problem, because it can get kind of complicated. So we set this up, and we get this setup where we have some x squared. We're going to assume that this minus x down here is really small, because typically the concentrations for most weak acids are small. This is what sometimes is called the 5% approximation. You do this whole problem out, and then you check the validity of whether or not you could remove this by then comparing it to what would happen if you didn't, and you do it the quadratic formula. This is excessive in most cases. The vast majority of cases, you're able to make this assumption correctly. The typical exceptions to this are when you have relatively strong weak acids like HF, or ones in that kind of ballpark of strength, times 10 to the minus 4, minus 3, minus 2. That's typically where this level becomes much more significant. Also, it's going to depend on how big your initial starting number is, because if this is a big enough number, this initial starting amount, which originally came from what was provided in the problem, how much of this HCN we started with, if you have a big enough number here, you're also able to ignore this minus x. So those are the two factors that you take in mind as to whether or not you can do this. The idea is that if you do it, you need to get an answer that's accurate to within 5% of not doing it. So it's kind of silly, because most books and texts tell you that you almost have to do the problem both ways and then check whether or not you could do it. So I typically on tests will tell you if you can make this assumption or not, and just tell it to you. But in real life and in other problems, your checks to see if you can do it typically are your size of this I value. The bigger it is, the more likely you're going to be able to make this assumption. And the size of Ka, the smaller this is, the more likely you're able to make this assumption. Okay. So going through here, we make this assumption, and that allows us to just multiply our Ka by this factor and then take the square root of it and get a number. So we were able to this way get the number 7.0 by 10 to the minus 6. And then we see that the HCN doesn't really change at all when we do that. So we don't see any real change. This is another way to test the assumption. If you go back to the starting amount and you put in your theoretical x and see how much this changed. If this changed by a significant amount, typically more than 5% of the value, then you can know, hey, I probably should go back and make some adjustments. So this is how you check. Another way you check is by comparing your number if you're not sure. That's what they do by checking the validity of simplifying, because x is not always negligible. Again, I've given you information to help you check for that earlier in your workflow process, but down here you can also check that. Species involved in the principal reactions, that's your main dissociation. Again, if you needed to get the OH minus concentration, you could do that this way. You could calculate the pH from your H3O plus concentration, finally down here, whatever you were able to obtain. And this is just talking about how you would be able to check the assumption that all the H3O plus comes from the principal reaction by comparing the magnitude of your H3O plus concentration to your to 1 by 10 to the minus 7 and see if that makes a big difference. They also show adding these two numbers together to see if there's any significant deviation in the source. But again, this is a little more extra just in checking. They give us a step through of all the processes, checking the big concentrations. Again, most of the time I'm going to show you a method that gets you the right answer. Especially when you're given multiple choice problems, you can typically just use this unless you see big standout things that suggest that you can't. And we'll look through that, because I know that it's hard to do all these steps every single time. It slows down doing these problems, and you're generally going to have to do them quickly for most tests and exams and situations. So I developed the Chasey quick and dirty weak acid, weak base pH, POH equation. So what you do is you take the negative log, the square root of K times the concentration. This quick equation makes all the assumptions you can possibly make and spits out a pH value or POH value. If this number is close enough, then you'll get the right answer. And a lot of questions just ask you for the pH of a weak acid or weak base solution. If you see that, then you can work it out this way and get a quick answer, and then you can move on. Especially if you don't have time to work out everything and check everything, this is the way to approach it. And most of the time, as we'll see as we'll work through more problems in this chapter, you can use this and get close enough that you're done. Again, unless you see some big red flags that tell you that you can't, if you have time, of course, you can always go back and double check and make sure. But on a test, I'll tell you, hey, this is one where you need to use the quadratic formula. We'll see that in a little bit when you can't make the assumption. But otherwise, I want you to be using this because when you take standardized exams, 90% of any weak acid, weak base problems will be easily solvable with just this equation. And so I want you to be quick with doing this so that you're able to get through those situations. Remember that pH plus pOH is equal to 14. So if you do this for a base and you put in the Kb, you'll get the pOH. So you can subtract that from 14 and get the pH and be done. So now you can quickly and easily get answers to these questions without having to set up an ice chart and do all of this. Again, it's not the correct way. That's why I call this quick and dirty and cheesy, right? It's not the way going through every single step, but it gets you this assumed answer. So you get some kind of base to start with. If you want to go back and do some more analysis, if you have multiple choice, you can pick the best answer and then you can move on. So here we have, again, we have HF. So that's one of our flags that, hey, maybe we can't make this assumption. Maybe we can't make this assumption. We can certainly still make the assumption that there's no H3O plus contributed by the dissociation of water itself, because that's 1 by 10 to the minus 14. And that's 10 orders of magnitude different here. So that's really important. We can make that assumption. So we set up our ice chart again as usual, and we plug everything in. Now, we can assume that this minus x is not important, but remember we've got HF, and typically that's like 1 by 10 to the minus 14. This is an example where we might not be able to make that assumption. Keep in mind, and we kind of knew that going in, because whenever we have to mess with HF, it's a strong enough weak acid that typically we're going to have to check. And how do we know? Because we look at the Ka. If the Ka is on the magnitude of like 1 by 10 to the minus 4 or greater, so minus 3, minus 2, minus 1, we typically won't be able to make this assumption. It might be worth just not using the quick equation and doing it all out or saving it for last or something like that while you're doing a set of problems, because it's likely you will not get the right answer. So they make the assumption and they get a value for x here, and they plug that back in, and they say that is known to the third decimal point. It's negligible compared only if x is less than this. Ours is not negligible. So we solve the quadratic formula. They don't bother to show you what the answer would be and how different it would end up being. So the answer you got from that initial step was 4.2 by 10 to the minus 3. And the real answer is 4.0 by 10 to the minus 3. Now that doesn't sound like that's off by a whole lot in real life, but when you take the pH, you will get a different pH number, enough different that could cause you to now miss the problem. Typically, if you're off by like, a 100th in the pH unit, you'll typically get through any kind of online homework questions or anything like that without any sort of problem. But if you're off by more than that, like a whole tenth, that can cause you to miss the whole problem. So something like that might throw you off that much. So it's important to realize this. So when you can't make the assumption, what you have to do is use the quadratic formula, right? So if you remember back from a algebra class, we can multiply both sides by everything that's down here in this denominator and reformulate this equation into this form. And that'll involve just multiplying this number by this. It'll be this times this step, and we spread everything all out, and we end up with these three numbers once we move x squared to the other side too. We set up the quadratic formula, so minus b, that's the coefficient on the x term, b squared, squaring this. So this can be very complicated to do. There are quadratic formula solvers online that can help you check your work. You can also do this in a calculator. Typically, I like to make the assumption of the positive answer first, like making this be a plus sign first, but that's just me. Sometimes you'll want to try the minus sign first. I try to make as much in the equation initially going in positive and only have negative on one term or no terms if I can, because that increases my odds of not making a sign error in doing this. We end up going through this and we end up with these two answers. Now, sometimes the negative answer is the right answer here, because x by itself is not per se a concentration in every instance. In this instance of our ice chart, x has to be able to be a concentration, so no negative x's are possible. But if you had more terms down here in these equilibrium concentrations down here in E, it might be possible for, or if x was negative, it might be possible for x to be a negative number. Sometimes when you're setting up equilibrium problems, like I talked about before, it actually runs in reverse, and so you put the wrong signs in the change. And so in that case, the negative answer might be the right one. It can depend. You want to plug these back into your ICE chart and make sure that in every step, when a real concentration is required, like the overall answer on the ICE chart, like an answer for initial concentration, the change can be negative, but these equilibrium concentrations, all these numbers have to be positive. All these numbers have to be positive or zero. All these have to be positive or zero. You can't have any negative numbers for a real concentration. Keep that in mind. That's how you can check, because only one of them is going to be the right answer. So only one of them is going to yield a positive value with a physical meaning in every instance, and only one of them can ever be the right answer. So that shows the difference that the quadratic formula can make and when you might have to use it. Again, if I have a question like this on the exam, I will mark it as such that you need to use the quadratic formula. That way, if you don't, I can still give you some partial credit, but you're going to lose some points because you didn't do it the right way. You can still get a close enough or close-ish answer without doing it, like you saw here. But when I tell you to, you should, so that you can get full points. Notice that in this equation here, if we look here at the answer, right, where they worked everything else out and they got the final answer of 2.4. Now, when I do this with the sloppy equation, I got 2.38. Look how close that was to the real answer. So it made a difference, right? It made a difference in the 10th place. It made a difference out here. But I don't know. This is kind of hard with a pH meter that you typically would have in a lab. And even with like an online homework or something, if you got this answer and this was the right answer, it'd be close enough. What I'm trying to say here is if you don't have time to do the quadratic formula and you think you might need to, you might want to put down the answer that you get from just doing this the quick way and then take your time later to go back and double check. So you don't lose a lot of points by doing this. Okay, so keep all that in mind. So percent dissociations, how does this work? So this is if we take the amount dissociated over the initial of the acid. So that would be, from like our previous examples, the value of that subtracted x. The amount that dissociated, so it was removed from the concentration of the acid, that value will go into this HA dissociated over the initial. And this percentage will help tell you approximately the strength of the acid in this particular instance, how much of it is ionizing. But this can vary with the concentration that you start with. Of course, dramatically, it's not a linear relationship. So it's interesting, but it's sort of a per solution measurement. It's not really something that you would want to reference for every acid or base unless you standardize the concentration you started with. Percent dissociation, as I say, decreases with concentration for weak acids. So as you increase the concentration, your pH may go down because this is an acid, so you're putting more acid in there, but the bang for your buck you're getting goes down. And that's why I was talking about how this is not a linear relationship. You can see there's a nice big curve in there, so that is not a linear relationship. And so you get about 4.2% dissociation, and it declines to 0.42% dissociation as you increase the concentration. And this is typical. Weak acids, as you increase their concentration, dissociate less as a proportion of how much weak acid there is. This is another way of saying the same thing. All right, so this is the end of this particular presentation. I will see you all again in the next one. Thank you.